and B k epsilon ijk with a negative sign is Fij. Okay? And that's not all. So what these equations obey, it obeys the divergence is the current and the Bianchi identity. And altogether, we discovered that these equations can actually be written purely in terms of one vector, which is the vector potential. And so what we discovered was that the Bianchi implies that F mu nu is the curl of the vector potential. And therefore, when you then plug it in, this was the equation for A. Okay? So that's actually the full content of Maxwell's equations, at least the electromagnetic field part of it. You will also need dynamics for the electric current, and for our case, it's the Dirac equation, but we'll come to that in a little bit later. Right now, I'm just trying to make contact with the something that you guys are hopefully at least somewhat familiar with. And later on, I'll give you a different motivation of how you might arrive at this. So, yeah, and so what we looked at, now what we tried to start looking at was the free electromagnetic field. By free, I just mean, or source free, that's just a better way to put it. Just means a homogeneous solution to this guy, okay? And so what we did the last time was to choose a gauge, but I did not justify it. So let me do it now before we return to the wave equation, right? So remember, we got a wave equation for A, but that was with a particular choice of gauge. But I didn't justify that, and so I should do that. So how do you justify it? So remember that this guy is invariant under the shift A mu replaced with A mu plus gradient of lambda, where lambda is arbitrary. Okay? So what that means is that I'm allowed to shift it by this amount if it did not obey the Lorentz gauge, and try to make it so, make it obey the Lorentz gauge. What do I mean? So suppose, remember the Lorentz gauge will not obey, Lorentz gauge not obey. Meaning, right now I have an A that is not 0, okay? So now I say, well, I can always use a different A. Let's call it A prime, equals to A mu plus partial mu lambda, okay? And now I want to see what happens to this. Well, this is now divergence of A prime mu is divergence of A mu plus partial square, the wave operator acting on lambda. So in my new, this is like the new gauge, right? New gauge potential, the new vector potential. This is the old gauge potential. So the old guy is not divergence free. This is not 0, but you can see I can now make this 0, the divergence of the new guy to be 0, by simply choosing that lambda obeys the wave equation in the following way, right? That is source partial squared on lambda is just equal to the divergence of the old guy. Okay, so it works just by choosing lambda to obey wave equation source by minus divergence of A, I'm just writing it in short form, we can make V render divergence of A prime to be 0. Okay, meaning the new gauge potential is now divergence free. So in other words, this is a proof that you can always do it, right? You can always do it because if you're not in a Lorentz gauge, then you can always make it so. And we remember that what we do is we consider all the gauge potentials that are related by a shift, by a gradient, to be equivalent. Right? So remember, A is equivalent to A plus partial lambda. So now that we have the proof, then we can say, okay, so now let's choose the Lorentz gauge, or let's use the Lorentz gauge. Okay, because now we've proven you can always do it. In your homework, what you would also show is that the freedom to do this is related to why this equation cannot be solved. So this is something that maybe I should say over here first, before we actually solve it. So the freedom to shift A in divergence of f mu nu equals to 0 is actually makes it the left-hand side non-invertible. We can't solve it because there's too much ambiguity, right? Like I said the last time, let's say you guessed a solution, okay, and it's possible, that you just look at it and you guess, and it's possible you write it down, you differentiate, you calculate, oh, is it equal to the right hand side, and it's equal to the right hand side, you solved it. But I will tell you, your solution is not unique. There's an infinite degree of ambiguity because I can just add a gradient to it, completely arbitrary, and it will still solve the same equation. So, so what do you make of it, right? How do you interpret it? So classically, you would say that doesn't matter. Your ambiguity is not important because all we can measure are the E and B fields. And so if you are very clever and you can guess what the solution is, it's all good. Just plug it in, take the curl, and calculate the E and B fields, and you're good, right? But if you don't know how to solve, if you can't guess, which is most of the case, right? If you can't guess the solution, then there needs to be a better way, right? And so what you discover in your homework for yourself is that this degree, this freedom to shift is intimately related to the fact that this wave operator here is not invertible, right? So if you write it out explicitly, this is actually partial squared. And then let me write it as Kronecker mu alpha, and then minus partial mu partial alpha. This is equal to that. And what I mean by non-invertible is that this guy there's no inverse, okay? Meaning partial squared connected mu alpha minus partial mu partial alpha inverse does not exist. How do you show something is not invertible? You show that there's a null eigenvalue, null eigenvector. If the null eigenvector means there's a null eigenvalue, and if you have a null eigenvalue, that means the determinant is 0, right? And if the determinant is 0, then we can forget about inverting it. So the best way, the easiest way I know how to do it is to do it in Fourier space, right? And then it becomes just a matrix equation, and you can see this very easily. So I'll let you guys see that for yourselves in the homework. But for now, I'm going to actually exploit the fact that I can always choose this guy, and now what you see is that the divergence part goes away, and this will become partial square a mu equals to 0. Okay? Actually, I'm going to do the downstairs guy. Doesn't really matter, but I'm going to do the downstairs guy. So remember, when I solve this, I want to also impose this guy, right? So n. Right, so that was both must be satisfied. Otherwise, it's not a consistent solution. I can then choose a different gauge if I want, but I will need to add to that solution whatever gauge transformation. Whatever gauge transformation is relevant. Oh, I maybe forgot to say. The shift is called the gauge transformation. So let me just write that down. Jargon. Shifting a mu by adding to it a gradient is a gauge transformation. Okay. So hopefully at some point I'm going to talk about non-abelian gauge theory. But this is very easy, but non-abelian gauge theory is a little bit more involved. You need to, again, do a bit of group theory. So I hope, maybe not right away, but I want to talk about QED first. But later on, I'll hopefully find the time to come back to talk about gauge theory. Gravity is also a gauge theory. But anyway, I hope that I at least talk about non-abelian gauge theory. Okay, so this means there are 4 wave equations. Yeah, because mu can run from 1 to 3. Okay, so immediately, in fact, if you remember, for the scalar wave equation, we were able to immediately deduce that phi as a function of x is the integral over k. Basically, you sum over all the homogeneous solution, the general solution. Remember that I pull out the 1 over square root k, 1 over square root 2k. This is just for convention. And then you have a tilde k e to the minus I k dot x plus complex conjugate. CC means complex conjugate. And k here, k dot x is k mu x mu, and k squared itself is 0, meaning k0 squared minus k dot itself. You guys remember this? So the reason is because when you apply, you remember that each derivative, when you apply it on a plane wave, is minus I k mu. Right? So if you just write down a single mode, so if you write down a mu tilde e to the minus I k mu x mu, you will find that it's the same. When you plug this ansatz into this equation, you will again find that k mu is, which I define as k squared, which is k0 squared minus k vector squared is again 0. So actually, we don't need to do a lot of work. That's why I did the scalar case first. So let me write down. Actually, let me erase that part. The only new thing is that now you have an extra index. For the scalar, there's no index. Alpha is just essentially alpha tilde over square root 2k is basically the Fourier transform of phi, right? It's basically up to a delta function is basically the Fourier transform of phi. But now for A, there's an extra index. In other words, there's a polarization vector that you need to associate with A. It points somewhere in space-time, right? A mu, remember, is a vector, so it points in a particular direction in space-time, and therefore, even after you go to Fourier space, you need to also have a vector that points somewhere, but now written in Fourier space. Yeah, every time I teach, you're going to hear me complain about markers, because I don't like markers. Yeah, because of all this, how do I get rid of that?
I want to
Yes.
make sure
Yeah.
does lambda depend on x?
Yeah. Yeah, it's lambda is completely arbitrary. Yeah. That's why I say there's an infinite degree of ambiguity, right? Because you can add. If I tell you I have a solution to my equation, but I can add to it any arbitrary function, the gradient of any arbitrary function, that's really ambiguous, right? Yeah, that's the nature of the gauge potential. I'll discover I need to work out more. I'm going to lift weights, maybe I'll be able to clean this more readily. Oh man, what is this? Okay, I'll write over it with a green marker.
Okay.
So A mu of x, we now know must be also a superposition of plane waves. So again, for convenience, you'll see why later on when I quantize it. I'll write this 1 over square root k. Remember, k for me is just the magnitude of the momentum vector. And then what I have now is that I need to have a polarization vector. And so what I can do is I can split my Fourier space A into polarization vectors that are normalized to 1, right? So I can have the sum over, let me call it epsilon s mu. So these are my basis polarization vectors. I'll write it down explicitly later. So this, for now, because there are 4 components, right? So it runs from, let's say, 1 to 4. Okay. And then, for each basis vector, I need to multiply by some coefficient, right? Because this is just the basis. So I need to write down alpha of s, and this may depend on k. Actually, even the polarization vectors might depend on k, but it depends on the choice. Okay, so again, this is just the decomposition of a vector in Fourier space into its basis vectors. So for example, if I choose a Cartesian basis, then epsilon mu, say 0, would just be 1, 0, 0, 0. And then epsilon 1 mu would be just 0, 1, 0, 0, and so on. Okay, let me just write it all out. 2 mu equals to 0, 0, 1, 0, and so on. Epsilon 3 mu will be equals to 0, 0, 0, 1. Okay. But so in this Cartesian basis, it's just a bunch of zeros and ones. If you want, I can summarize all of this into epsilon s mu is actually just Kronecker s mu. Right. That's a summary of what I'm writing over there. But later on we'll see. I think I'll first finish this discussion. But later on we'll see that there is a different basis that would be k dependent. But we'll come to that. So basically, the alpha, as you can see, is just going to give this component alpha 1, alpha 0 is going to give you a different arbitrary component for this guy. Alpha 2 is going to give you an arbitrary component for this, and this, and so on. Right? So this is just a different, it's just a decomposition of this, just to be clear what we're doing. And in fact, I should write down 1 over square root 2k because I've written this guy down. So remember, this is arbitrary, so it's okay to normalize it differently. Right? And the reason will become clear as I continue. So now, remember, I'll just need to sum over the polarizations, and I will get epsilon s mu e to the minus I k dot x plus, again, complex conjugate. Okay, because this is a real object. So once you've written down e to the minus I k dot x, you don't have to write down the other guy. It's just, it has to be the complex conjugate. Otherwise, it wouldn't be a real thing. It wouldn't be a real object. But again, remember k dot x is k mu x mu, and k squared is always 0. Okay? So that's in fact the solution. But we already, well, we have one more thing to do, which is that we remember that we got here by imposing the Lorentz gauge. Right? And the Lorentz gauge is this guy. Okay, so this comes from the wave equation. This is the wave solution. But we also need to impose the Lorentz gauge. Okay. And so remember that k partial mu, once you bring it inside the integral, becomes minus I k mu. Okay, so what you see, as we're going to discover, is that this Lorentz gauge is going to get rid of a combination of some of these vectors. Okay, so this is where the k dependence comes in, and so it's better for me to, in fact, do it for a particular momentum mode. So you guys will see what's going on. Okay? Let me try again. Just okay. So let's focus on the K mode that does the following. So let's focus on the mode, K mode that points only in the z direction, okay, just for simplicity. So it's going to be k, and then 1, 0, 0, 1, okay? And so what you discover is that, and then what I'm going to do is I'm going to rewrite because my basis, I can rewrite my basis in any way I want, right? So I can simply say that epsilon, instead of epsilon 0 and 3, let me modify that to write as epsilon prime of 0 to be a linear combination of epsilon 0 and epsilon 3. Okay? And this would mean, as you can see, it's just from the square root of 1, 0, 0, 1 transpose. And then I'm going to define epsilon prime 3 to be 1 over root 2 of epsilon 0 minus epsilon 3. Okay? So that now I can rewrite this sum not over these bases, but sum over epsilon prime 0, epsilon prime 3, and I can still retain the 1, 2 if I want. Okay, so this will become 1 over root 2, 1, 0, 0, minus 1 transpose. Okay. So why do I do that? Because the Lorentz gauge tells me the following. It tells me that K mu dotted into epsilon, remember these are linearly independent bases. So each of them must obey this. Okay, again, because each derivative gives you K mu, so that means that when I take a derivative of this, I'm dotting K mu into this object. But all of them are linearly independent. And because they're linearly independent, they must each obey this. Okay, so because epsilon as mu is linearly independent. Okay? And so let's see. Well, for epsilon 1, 2, we can actually see quite easily that it's automatically satisfied, which is why I chose the k to point in the third direction. Why is it automatically satisfied? Because it has only components in the 1 and the 2 direction, and 0, 0 in the 0 and 3 direction. So when you dot it with this guy, it's automatically 0. This is automatic. Nothing to calculate, basically. But now, if I dot it into this component, this basis, K mu epsilon prime 0 mu is what? It's actually K and then 1, 0, 0, 1. And then this is mu upstairs. I define it up to be upstairs. Will then be dotted into 1, 0, 0, 1 mu downstairs, right? So I define this downstairs. You can define it up or downstairs all you want. You just have to be careful when you dot them together. You will have to move one of the indices, right? And it will cost you a minus sign in either this one or this one. So that's why, for simplicity, I just define them one up, one down. So this you can see right away gives you k, and then there is a 1 over root 2, right? So there's a 1 over root 2. So it will be k over root 2 times 2, which is basically root 2k. Okay, so in particular, this is not 0. Whereas the other one will be 0. Let's do that first, and then I'll tell you what the result is. K mu epsilon prime 3 is what? Is now, again, K 1, 0, 0, 1 mu 1 over root 2 And then the other guy will be 1, 0, 0, minus. Remember when we were doing our group theory, what did we do? What did we say? We said that if we look at the, so let's write this down. So recall the group theory. Or the representation theory of the Poincare group. In particular, our discussion of massless spin 1. Okay? So here we're doing it from the classical field theory perspective. But remember when we're talking about the representation theory of the Poincare group for massless spin 1 particles, how did we arrive there? What we showed was that when you study the representation theory of massless particles, you cannot boost to the rest string. So at most you can choose a reference momentum that points in the z direction. That was our reference momentum in our discussion of the group theory. This was the guy, in fact. And then, we didn't show it in detail, but I explained that Wigner showed that to study the representations of the group, you only needed to study the representations of the group, of the subgroup, that left this guy invariant. What was that? It turned out to be both the rotation group in the 1-2 plane, as well as a mixture of boosts and rotations in the third direction. It was a combination of the two. But in our case, as long as you don't care about infinite spin, continuous spin, as long as you don't care about continuous spin, we only needed to study SO2, the rotations around the 1-2 plane. Okay? And that, in fact, is what led us to the concept of massless integer spin, or integer or half integer spin. And in that case, in the integer case, we found that there was a plus or minus 1 helicity. Where does the plus or minus 1 helicity show up? It's exactly these guys here. Okay, so these guys are exactly. Okay. So now what we've shown is that actually embedded in the Maxwell theory, even at the classical level, we already have these helicity modes, right? And in some sense it has to happen because remember that we are working with the Lorentz covariant theory. And so if it obeys Maxwell's equations, essentially at some point you're going to discover the classical limit of massless helicity plus or minus 1 particles. And these are the guys, okay? And so what in your homework you'll do is that you'll find that you can actually write down using these guys, the 1 and the 2, there's a way to write down a linear combination of the 1 and the 2 in such a way, let me just call it C1 and C2. It's a 1 and an I somewhere, I cannot remember right away, but in your homework you'll discover for yourself that by taking a linear combination of 1 and 2, complex linear combination, you will find that under rotations in the 1-2 plane, so you will discover that two things. One is that the Cartesian basis that we write down, epsilon 1, 0, 1, 0, 0, and epsilon 2, 0, 0, 1, 0, these are basically linear polarizations of the electric field. So if you compute what is the electric field produced by this guy, you'll find that, well, it is epsilon 1, then the electric field is oscillating in the one direction. If you look at the epsilon 2, then the electric field is oscillating in the two direction. Now, if you change it to this particular helicity combination, then you'll find that the classical limit of helicity, the concept of helicity, actually corresponds to circular polarization of light. So let me just write this down. This corresponds to the circular polarization of light. Okay, and what you discover is that not only that, what does circular polarization mean in the group theory language? Remember that what it tells us is that it's an eigenvalue of the plus or minus 1 is the eigenvalue of the generator of rotations. And so if you rotate this, guys, if you rotate epsilon plus minus around the around the third axis, right? That's basically performing a SO2 transformation on the 1-2 plane. What you will discover is that this should act like e to the minus I theta j, acting on epsilon plus minus. But if these are the eigenstates of j, then what you will get is that you get this to be plus or minus plus I theta plus epsilon plus minus, right? It's minus plus because, again, if this is supposed to be the eigenstate of j, you should get these two eigenvalues. And in fact, you will show it is in fact the case. By taking an appropriate linear combination, you will not only get circular polarization of light in the classical limit, you will also be able to find, by doing an explicit calculation of rotation, you will find that you get exactly the helicity eigenvalues. So you discover the meeting of these two analysis, right? You solve the equation exactly, precisely, and you get out the helicity modes. But those are the helicity modes that you exactly predict from just group theory, just from studying the symmetries and understanding what should you get out of the representations. Any questions?
So it corresponds to U1 symmetry.
That's right. So that's the next step. How does this correspond to U1? We'll come to that. Unfortunately, I ran out of time, but yeah, I'm going to talk about it after this. U1 has to do with the fermionic sector, right? Because there's no U1 here. Everything is real. Right? A is real, and everything is real.
But we can identify two numbers to one.
Come again. Sorry, come again.
But we can identify two real numbers to one complex number.
Yeah, but it doesn't show up here. So U1 explicitly shows up because of the fermions. Yeah, you are rotating it by a U1 transformation, and and how that interacts. How does that show up? How does it connect to the vector potential? It's very much related to how what the difference is between the partial derivative and the covariant derivative in differential geometry. Right? You need to introduce a Christoffel symbol. Likewise in here, when you take a covariant derivative on the fermion, you discover that you need to introduce the gauge potential. And the more, so this is for U1, and the more complicated version of that will be to introduce a non-abelian gauge potential. If you apply a non-abelian gauge transformation on the fermion. Yeah. That's what SU3 and SU2 means. Basically, you're taking, SU3 means you're rotating 3 species of quarks, right? Red, blue, green, I think. And I forgot the color. I think it's blue, green, but there are three of them, right? You rotate it amongst themselves using the SU3 group. SU2 means you rotate the neutrino and the electron, or the muon and the muon neutrino, and so on. Yeah, but that requires that you know about the fermions. Otherwise, the gauge fields themselves, at least in the EM case, you don't need to worry about U1. Yeah, but there is a connection, right? In nature, there is a connection. Yeah. Other questions for me? No? Okay. See you guys on Wednesday.